is sealed as the piston moves up. The volume in the crankcase gets bigger. That draws fuel and air into the crankcase. When the piston moves down, it reduces the volume and pushes that fuel air up into the combustion chamber through, as somebody pointed out, a port in the crankcase. There's no, in the combustion chamber, there's no valves. So how is gas flow in and out of the combustion chamber controlled in a two-stroke engine? Two-stroke. Here we go. Ports right in the side of the cylinder wall, right? These ports get covered and uncovered. Yes, so the reason we need this check valve is because this isn't showing it, transfer port. This is a little bit different design. There is a check valve into the crankcase. This is a little different design. Most of them use a check valve into the crankcase so that the intake, so that the fresh fuel and air inside the crankcase doesn't just blow back out the carburetor. There will be a check valve there. All right, I don't need to go too deep into this. What do we need to know? We need to know that gas flow in and out of the combustion chamber is controlled by ports in the cylinder wall. We need to know that two-stroke engines produce more power. Do you know why they produce more power? Right. Every downstroke is a power stroke. So in theory, it should make twice as much power. In practice, it's not that good, but it's significant. What are the advantages of a two-stroke engine? List all the advantages. Better power to weight. We just got that. What else? Simpler, lighter, work in any orientation. So where do we find two-stroke engines today, for the most part? It's not in aviation. Chainsaws. Dirt bikes are pretty much obsolete. It's almost all four-strokes in dirt bikes and go-karts. Chainsaw, basically equipment that you carry. Chainsaws, weed whackers, leaf blowers are kind of the last places that I can think of them. Occasionally there are some boat engines, but not many. Okay, so what are the disadvantages? Why are they not that popular, actually? They're inefficient, yeah. They're very dirty, more than inefficient. They pollute a lot. They burn the oil, right? And they don't last very long. Why don't they last very long? Right, what's the lubrication system for a two-stroke engine? We just add oil to the fuel, right? And that's not a very good lubricant. All right, so that answers the last question. We just spent a bunch of time talking about oil and all the great things we can do to oil. And then here we have two-stroke engines that basically don't have oil in them. Okay, just a little bit of oil mixed in with the fuel. Okay, what causes the fuel to ignite in a diesel engine? Heat of compression, right. Where and when is fuel injected into a diesel engine? Right. Directly into the combustion chamber. Very different from most gasoline engines. When do we inject it? Well, basically at the same time as we would light a spark in a gasoline engine, that's the same time that we inject fuel in a diesel engine, right at top dead center, right near top dead center. Okay, so what fuels can a diesel engine burn? Jet A, kerosene, diesel fuel, yes. You might notice if you go to the airport that there's a disproportionate number of diesel cars and trucks in the parking lot. That is because when you take fuel out of an airplane, a jet airplane, they can't put it back in the airplane, and so it is very typical to give it to the mechanics, who then put it in their diesel trucks and diesel cars and drive around for free. So big reason that diesels are gaining traction in light aviation is that it's getting harder and harder to get avgas. Oh yeah, I put several hundred gallons of jet fuel into my last truck. Okay, so flying to remote airports, you can almost always get Jet A. You can't almost always get avgas, and if you can't find avgas, your airplane doesn't fly. So fuel availability is one of the main reasons that they're talking about moving to jet fuel for a lot of aircraft. It is cheaper to operate, and that the fuel is you get more miles per gallon out of a diesel than you do out of gasoline, and the engines last a very long time, but the main driver is fuel availability. Okay, what is the difference between piston displacement and total volume? And this one will always catch a couple of students. If my engine has a clearance volume of 10 cubic centimeters and a swept volume of 70 cubic centimeters, what is the compression ratio? Clearance volume of 10, thank you, 8-to-1, because the total volume is 8. And that goes down to 1. Okay. What is the difference between piston displacement and engine displacement? Nope. What's the difference between piston displacement and engine displacement? Correct, Braden. All pistons combined. So if I give you the piston displacement and then tell you it's a V8, you got to multiply by 8 to get the total displacement. Okay, compression ratio. What does compression ratio describe about an engine? Okay, we just actually talked about that. I think, yeah. Compression to power. No, it just tells you that relationship of how much. Yeah. Volume you've got at top dead center and how much volume you've got at bottom dead center. Okay, how are compression ratios calculated? We just did one. I asked a question. Is anybody need some more help understanding how to calculate a compression ratio? Nobody? Yes. Okay. Let me pull up a PowerPoint here and go through the whole. Hey, maybe if I pull this down here when I start my slideshow, I won't need to switch it. And nope, still got to switch it. And there we go. Get my pen. If I've got my cylinder here and I've got my piston here, and do another cylinder here with my piston here. Here is what we call my clearance volume. And from there to there is my swept volume. So this plus this is my total volume. So if this is 7 and this is 1, this would be 8 to 1. Does that work for you if I draw it out like that, Aiden? Okay. All right. Now let's find my Word document. Put that back. Here's what I'm going to do. This way works better. Okay. So now are we good with the first two questions? It's just a ratio of total space to compressed space. Yeah. Okay, so what's the advantage of using a high compression ratio? Better fuel efficiency, right. Do we get more power? Yeah, you don't get more power out of, not necessarily more power. You get better fuel efficiency. And so there are some very powerful engines that have quite low compression ratios, especially if they're turbocharged or supercharged. This is where you read more power. Yeah, it's more fuel efficiency. You can make a powerful engine with low compression ratio or high compression ratio. But if you get into the physics, you think about it, if we can expand the fuel air mixture twice, like a 2 to 1, you could get a certain amount of energy out of the hot air, right? If you could expand it 4 times, you can extract more energy out of the expanding gases. So the more compression ratio we've got, if we've got a 20 to 1 compression ratio, we get a lot of the energy out of the fuel and air, but it's not directly tied to the amount of power we can get out of it. Okay, so here's an example. Which has a higher compression ratio, gasoline engines or diesel engines, Braden? Diesel, way higher. Which makes better power, gasoline or diesel? Which makes better power to weight, gasoline or diesel? Ooh, you ever see any racing motorcycles or race cars with diesel engines? No, gasoline makes better power to weight. What is diesel good for? Long haul trucks, right? Torque and long haul trucking. What is a long haul trucker worried more about, power or fuel efficiency? They're way more worried about fuel efficiency. Diesel trucks aren't terribly powerful. What's let's look this up. What is the power of a diesel? Just pull this down so you can see what I'm looking for here. Let's look at a diesel tractor, not tractor, Freightliner. Freightliner engine power. How much does the Freightliner engine have? 600 horsepower. So is a 600 horsepower engine really that powerful when you consider how big the truck is? Not really. What they're after is fuel efficiency. So getting back to our original question here, high compression ratio gives us very good fuel efficiency. So why don't we just run 20-to-1 compression ratio in our gasoline engines and make them just as efficient as a diesel engine? So it just said that we get great fuel efficiency out of high compression ratio. Detonation, exactly. So why don't diesel engines have a problem with detonation? Why can we use a high compression ratio in a diesel, but not in a gasoline engine? Because they detonate on purpose? No, we don't. Detonation is the explosion of fuel and air in the cylinder, and we never want an explosion. We always want a smooth burn. Explosion damages stuff. Smooth burn doesn't. Aha, I seem to have come across a misunderstanding here. Don't explode. Okay, but we don't want an explode. We want detonation. What do we compress in a gasoline engine? What do we draw in when on the intake stroke? Fuel and air. Right. And then we compress a fuel air mixture, and if it gets too hot, it'll explode. What do we draw in on a diesel engine? Just air. So if you compress just air, will it explode? Of course not. When do we inject the fuel in the diesel engine? At max compression, right, near top dead center. And we compress it, we can spray it in, but it can only burn as fast as we spray it in. So it literally can't explode. It can only burn as fast as it hits the hot air. So diesel engines never detonate and never backfire because all we're compressing is air, and so they're incapable of having those two problems. So high compression ratio gives us great fuel economy, and we would use high compression ratio in a gasoline engine, except that we can't. That does that help, Braden? Trying to sort out. I can tell you're trying to sort of sort out all the different things we're trying to do here. Aha. So what happens if the pressure gets too high? Detonation. Yeah. Yeah, pre-ignition is a little different, and that article is really good. The high pressure won't typically cause pre-ignition. It's not quite enough to set that off, but it will certainly cause detonation because of high compression ratio or supercharging. That work for you, Mercan? Okay. So moving along. We're on page 4 of 5. Hey, we're moved through most of this one. Okay. What's the difference between normal combustion and detonation condition? What is the difference between normal combustion and detonation? The next question here. Right, maybe I'll draw this a little bit. I'm not sure how Mr. Cliff explained this, and if I'm saying the same stuff and we're not, oops. Okay, so let's draw my combustion chamber. Actually, let's draw it in black because Here's my combustion chamber. Here's my piston. Up near top dead center, there's a couple of piston rings. There's a connecting rod. Off. Okay. What I've got in here is, let's put myself a blue mixture of fuel and air. This is all in my mixture. And I'm going to just draw one spark plug off at the side. This will be not our best engine design yet, but here's one off at this side. Now we're near top dead center, and we're going to make this, let's make this a 10.5 to 1 compression ratio. This is a high compression ratio engine, so it's going to be real prone to detonation if we don't have good high quality gas. And we're going to light our fire here. And some dingbat bought themselves a 10.5 to 1 compression ratio engine, and then they went to the gas station and they tried to save $5 on a tank of gas and bought cheap gas. Okay, so we light the fire and we get a flame front coming across here. Now we're talking microseconds here, right? The piston is moving up, the flame is moving across. What do you suppose is happening to the temperature and pressure of this, we're going to call it end gas? What's happening to the temperature and pressure on that end gas? We've got 10.5 to 1, so we're already at 1500 degrees. And now I've got a wall of flame pushing on it and squeezing that end gas. It compresses it even further. If we've pushed beyond the limit, what's going to happen is all of this end gas will explode. And I've got a perfect example of a piston in our shop that is nice and clean and in good shape. On this side, the piston's in good shape, and on this side, it's all beat to heck. It's pitted, it's melted, it's rounded, and you can see that what happened is the flame was going across and we were getting good combustion, nice happy piston, and over here it was just getting hammered. So that's the difference between normal combustion. In normal combustion event, what we should have is just this flame front that continues across normally, and we've got a happy engine. And that's supposed to be completed just a couple of degrees after top dead center. Okay, so that is detonation. What do we do if we've got detonation? What do we do to stop it? What are some tricks? A modern car engine has got a sensor that will listen for this knocking. And what it will do is it'll protect itself. You won't actually end up with engine damage. You'll just end up with poor fuel economy. Rich mixture, that's one. And we'll talk about this a lot in next week after next when we get into fuels and carburetors. Adding fuel, oddly enough, cools things down. Basically, because we're not adding oxygen, we're just adding gasoline. And if you add more gas and no more oxygen, the mixture gets cool. The whole thing gets cooler. And that can help make the difference for an engine that's detonating. The other thing we can do is retard the timing. Don't start the spark. Don't light the spark until later. Both of those things reduce fuel economy, and the delaying the spark also reduces the power, but it protects the engine, so it's worth doing. Okay, back to our Word document. Okay, so does that help explain normal combustion versus detonation? I don't know, did Mr. Cliff show that picture? Or something like that? Okay, all right. So how does the correct selection of spark plugs help prevent pre-ignition? Used a good one. I don't even know what you're talking about there, Aiden. Use the right spark plug? Nice. Or were you trying to compliment me? I can't tell for sure. Okay, so spark plugs. What we're mostly concerned about is heat range. What happens if I pick too hot of a spark plug? What happens if I use too hot of a spark plug? Not sure. It acts as a glow plug. Right, if it can't shed its heat, it might actually start to glow. Then what happens is halfway up the compression stroke, the spark plug is so hot that it actually lights the fuel air mixture like way early, like 50, 60, 70 degrees before top dead center on the compression stroke. That is immensely damaging to the engine because now the fuel air mixture is burning and we're trying as we try and compress it. And that's just so much heat on our piston for so long that it will literally melt a hole in your piston in under a minute. Okay, so that's if we use too hot of a spark plug. What if I use too cold of a spark plug? Shouldn't that make the problem go away? How could using too cold of a spark plug cause a hot spot? It will get destroyed. No. We'll talk about spark plugs next week when we get into the ignition system. No, it's still sparking. Okay, so what can happen if you use a cold spark plug is if it doesn't stay hot enough, it will get fouled with carbon and oil and whatever. And if it gets fouled with carbon, that carbon can actually catch fire. And then it will act as a glow plug. So if we're too cold, the spark plug gets dirty, gets carboned up, and then can start to glow in between cycles. And if it's too hot, well, it's just too hot. So either way can cause problems for pre-ignition. Retarding the ignition event, how does that reduce detonation problems? Well, if you looked at my picture, if we light that spark a little later, there's less time for that compression and heat to be acting on the fuel, and we don't have as much issues with detonation. If we do it earlier, we've got more time that heat and compression is all acting on the fuel, and there's more chance of it inadvertently lighting off. Does that answer work for everybody? All right. If you're not understanding, pipe up. Which one? No, which am I trying to explain? The spark plugs? All right, well, let's pull up my picture here. Okay, so my spark plug. Let's get my spark plug. I'll get a little pointer here. There's the business end of my spark plug, right? It sheds its heat. It sheds its heat into the cylinder head. So this part here gets extremely hot because of the flame, and it's got to shed its heat to the cylinder head. If we don't provide an adequate, and we mess around with this cooling path to try and keep this at the steady temperature that we want, if we have not enough of a cooling path, this will get hotter and hotter and hotter. Remember, not only is it exposed to flame, it's actually got a spark. Like, this is a really hot part of the engine. Potentially one of the hottest parts of the engine. And if we don't make an adequate cooling path for it, it will get overheated. It will just simply start to glow. And then when the piston is moving up, it's surrounded by fuel and air, and it will just light it'll light the fuel and air when we didn't want it to. So that's too hot of a spark plug. If we don't get it hot enough, carbon and soot and crud will collect on it. Now, these are all flammable materials. So it's too cold. It's not burning itself clean. The carbon and soot collects up, and eventually it starts to glow and then causes the problem we were trying to prevent with a cold spark plug. Does that answer your question, Travis? And Mert can. Okay. Now, the question about the retarding and advancing ignition. Let's just go to my spiral here. When do we light our fire? "25 degrees. What if I made it 30? Would that be okay, so going back to this, looking at the chat here. Too hot or too cold is not good for the spark plug. Too hot, things melt and cause pre-ignition. Too cold, the plug eventually actually catches fire and gets hot. So the answer, Isaac, is we want a spark plug that is just hot enough to burn itself clean, but not hot enough to light the fuel air mixture. That make sense? Goldilocks zone, exactly. So is 30 advanced or retarded compared to 25? Advanced, correct. When would we want to advance the ignition? When we're running faster or slower? Airplane engines don't do this. Every other engine in the world does it. The faster you turn the engine, the more you advance the timing. Because we're trying to leave the same number of milliseconds, remember here, 13 degrees after, we want the burn complete. So we've got this much time from here to here for the burn to happen. And if the engine's turning fast, we need to give it a few more degrees. We need to advance it. But that can cause our problem of detonation because we've got more time acting on that end gas. Retarding it, we end up with less time of the heat and pressure and less total heat and pressure actually acting on that end gas. So this is to answer the next question of how does retarding the ignition event reduce detonation problems? It puts less pressure on that end gas and less time for the heat and pressure to act on that end gas. Setting it too early, obviously the opposite. Does that, by lighting it later, yes. Take it to an extreme point. Let's light it after top dead center. We'll hardly put any pressure on that end gas, right? Much understand, very comprehend. Oh, good. Good. Yeah, there's some cool stuff that I'd never really even thought about, before I taught this course, actually. I've learned a lot teaching the course here, and I'm trying to pass that along to you. Okay. Advancing would be to do it. Advancing the timing is just what we talk about. It's the term we use. I don't know why we use the term, actually. We do it sooner. Retarding means happening later. That one's easy. Retarding means late. Advancing, I don't know why they use advancing to say early, but that's what they do. Okay, so why are engines run rich at high power settings? I did talk about this. Why do we run engines rich when we're working them hard? To avoid detonation. And how do they prevent detonation? Keeping it cooler, yes. And why does adding more fuel make things cooler? Because there's no extra oxygen. Yeah. So imagine you're standing in front of a flamethrower and you got this flamethrower blasting on your face and you're Iron Man, like you can take it. And there's a flamethrower blasting on your face. And it's a perfect stoichiometric mixture of fuel and air. Every oxygen is getting burnt, every fuel is getting burnt. And then somebody goes and adds more oxygen to this. Will it get hotter or cooler? Why would it get hotter? It was a perfect fuel air mixture. I just added something to it, but I didn't add any fuel to burn. I just added oxygen. Does that not make sense? Oxygen only burns in the presence of fuel, and fuel only burns in the presence of oxygen. So if we have a perfect mixture, we get a really hot flame. If we add more fuel or more air, it gets cooler. Does that make sense? Like there's going to be a hottest temperature where we mix the perfect amount of fuel with the perfect amount of air. That's going to be the biggest flame when I've got the perfect amount of fuel for the perfect amount of air. Does that make sense, Braden? Adding more air is kind of the same as adding less fuel for the mixture. If you just add oxygen and don't add any fuel. What is more effective, for a few reasons we'll talk about, is to add more fuel, because the fuel starts out as a liquid and it's got to evaporate. That takes a ton of energy. And running lean has got a whole host of other problems. So we could run really lean at high power settings, except there's a bunch of other problems that happen, and it ends up destroying the engine. Adding more fuel cools things down because there's no oxygen for it to burn. It's just going to boil. Okay, so your flamethrower is aimed at Mr. Iron Man's face. It's hitting, 3,700 degrees, and we decide to add more gasoline to the mixture. All the gasoline can do is boil. It can't burn. It'd be like adding water to the mixture. If you added some water, the water would just boil, but it wouldn't burn. And it cools off Iron Man's face. Okay, which engine parts are commonly damaged by detonation? You're going to wreck a crankshaft, or you're going to wreck a piston rings. What about the ring lands? That space between the rings. They get pretty torn up. Valves can get damaged. Yeah. All right. Causes of pre-ignition. Well, we've talked about this. An ember somewhere in the cylinder, a ember on the spark plug, too hot of a spark plug, or a fault in the ignition system causing it to send a spark at the wrong time. All right, don't worry about how the cylinder bore is measured. We're not doing that right now. Where does most cylinder wear occur? Top, bottom, left, right? Correct. How would this affect a choked cylinder? Yeah, it will get rid of the choke. The choke will disappear. Why does the most cylinder wear occur at the top? Just out of curiosity. You think about that? That's where combustion, highest heat, highest pressure. Yeah. Okay. How are valve springs tested for strength? Oh, and I need to tell you this one. directly because we didn't do it in the classroom, and normally we do. You take it to the test bench, and you should write this down. There's a special tester we've got with a little spring-loaded with a little arm on it, and there's basically a ruler on the side of this tester, and you compress the spring to a specific length. So I take my spring, which is normally 2.5 inches, and I compress it down to 1.5 inches, and I see how much force it pushes back with. All right? You should write that down. Compress the spring to a specific length and check and measure the force that it takes to do that. Everybody got that? All right. How do you check a crankshaft for straightness? V-blocks and rolling it on a surface isn't going to work real well on a crankshaft because it'll go thunk, 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 thunk because of all the crank pins sticking out. Dial indicator. A surface plate would be useless. What is a surface plate? It's a flat surface, right? We use V-blocks and a dial indicator. Let's pull up a picture. V-block and come on, no pictures here. There's V-blocks. And here's a picture of a dial indicator measuring how round something is. So this little pointer moves back and forth. Here's a good picture. There we go. They're not using V-blocks, they're using a mandrel. But this dial indicator, you can see if this had any wobble, the dial indicator. Braden, nailed it. Thank you. You put the oh, I see. You're saying you put the blocks on a surface plate. Okay, fair enough. Fair enough. I got you for that. Okay. There's your mandrel, and we're going to twist this, and we're going to watch. And if we've got a perfectly straight shaft, this needle shouldn't move. Shouldn't move back and forth more than, a thousandth of an inch. Okay, back to my Word document. What do you do with a bent crankshaft? Anybody? Donate it to your local technical college. Correct, you can't straighten them. Connecting rods. How are connecting rods checked for straightness? Arbors. Thank you. There's a couple of questions that look at these arbors. Take a look at the pictures and understand how an arbor goes and where it goes. It's referenced pretty directly. We never do it in the classroom, so the questions are totally valid with or without what we're doing. So take a look at those pictures of how the arbors work. And they were in the PowerPoint. I know Mr. Cliff talked about it. What do you expect when you're measuring a campground piston? What do you expect when you measure a campground piston? Yeah, but what about the diameter? Yeah, it shouldn't be round. It should be oval. Does that indicate a problem? No, that actually indicates that it's the way it's supposed to be, right? A campground piston should be oval. This is normal. If it's not oval, you'd have to worry about that. How would you check piston pins for straightness? Well, that would be back to our V-block and dial indicator. When you're inspecting a valve, what's the most critical area to check? Face, the tip, yeah, face, the tip, and the head. Exhaust valves, you need to look at the head to make sure it's got a nice even pattern. The face is the sealing face, and then the tip. Yep. If you find pitting on the valve face, do we check all long stick-like objects with the V-block? Yes, pretty much. That's the best tool for, yeah, all, like anything that looks like a pool cue in any way, shape, or form, we put it on V-block and give it a dial indicator. Yeah, you can grind it. Wow, hey look, we're done this one. How are we doing? We just took a break, didn't we? Came back at, how was a piston, the connecting rod checked for straightness? Piston pins, V-block, and dial indicator. Was it? All right, so should we take another break? It's kind of a natural break point.